All right, so the last problem type I'm going to go over with you guys today, sample problem type 4, I'm going to do with you on Monday when we get back from the weekend. But this is where you're given just one, again, initial concentration, and you actually are given the equilibrium constant as well. But now you're being told to find all of your, again, multiple concentrations. Okay, so remember, if they say find the concentrations, plural, you know you're going to have to do an ice chart. Okay, so let's look at the setup here. And this is a type where you have an X in the problem. So you're going to be setting up a problem to find a variable. So mathematically, it's going to be a lot more work, but the math itself is pretty simple. It just takes some time to do. You're not really using anything beyond Algebra 1 skills of distributing and solving for an unknown. So here's your given reaction. You have two nitrogen monoxides. It's breaking down into nitrogen and oxygen gas. You're given your equilibrium constant of K is equal to 1.2. And you have moles of NO. We're in a 750 ml flask. So if I see that the flask isn't 1, what I would do right away is change my moles into molarity. So we're going to do 0.5 divided by 0.750 liters to get my molarity. And we have 3 sig figs, 4 sig figs, so I'm going to go with 0.667 capital M for molarity for that, okay, instead of using moles here. And it says calculate the equilibrium concentrations, right? So in terms of problem, it looks very simple because you're not given much information to start with. But just by the fact that they mention find the concentrations plural, I know that I have to make an ice chart. Okay, so this ice chart is set up a little bit differently than the last one that I set up with you guys. And this one, I think, is the way that I actually prefer to set it up. I just wanted to give you guys two options. So you actually write out the chemical equation on top. So you have 2NO, and here's your equation. It's N2 plus O2, right? And I put in all the coefficients here. So it's 2, 1, and 1. Okay. And this time you're going to put the ICE, the initial, the change, and the equilibrium vertically, right? And it's the same thing. We're still setting everything up. And again, I like to draw in a line to indicate the difference between my reactant side and my product side, just like what we did before. Okay, so we're going to plug in what I can. I start with 0.667 moles of NO, right? So I know that has to be initial. And it's molarity, right? And it says calculate the equilibrium concentration. So you use this number, you don't have anything else to put in, right? So it looks like we don't have anything, but just like last time, if they don't give any information about the other stuff, you know, you're just starting off with 0, right? So you're given a reactant, you're not given anything for the products, right? And before, the problem was a little bit different because one thing was given at equilibrium, so you were able to calculate the change, which led you to the other changes. This time you have nothing, right? You have nothing else to plug in here. So when you get to the change part, this is where you just throw in x's. It's xxx. I don't know what the change is, right? And just like before, your change row is going to be determined by the coefficients. So I have a coefficient of 2, so it's not just x, it's going to be 2x. That's 1, so it's 1x, that's 1x. You could write the ones if you want, right? And the changes, it's not just that, it's just a random number here, right? It's going up or going down. So remember for the last problem that I did with you, the change was vertical this time, but same thing, you had a negative change, it was going down, and the other side was positive. And remember how I told you guys how if you have 0 amounts of stuff, the only change that you could have is that it can only be positive, right? You can't ever go to a negative quantity of stuff here when you're dealing with concentration. So here I see that I have a 0 here and a 0 here, right? So what does that tell me? I know that my entire product side is positive x, positive x. The reactant side is going to be opposite. So this guy here is going to be negative. Okay, so now we have some stuff we could work with. For the equilibrium row, we just take this and we summarize it. It's 0.667 minus 2x here. And then this is 0 plus x, so it's just x. 0 plus x, just x. Okay, so we have this. Now, if you finish this off and said, this is my answer, these are my equilibrium concentrations, it doesn't really mean anything because these are just x's, right? We're going to actually solve for what the x's are because this time we know what the actual k is. Okay, so let's go ahead and set this up. And again, just to warn you, the math is a little bit long and I'm probably going to show more work than what you're going to show, but I want to kind of spell it out for you guys a little bit so it's easy to follow in the beginning. So make a K equation. You guys know that Kc is going to be equal to products minus reactants. I have products N times O2 divided by my NO, and my coefficient is 2, so that becomes a squared on top. Okay? Now remember the point of this equation. They're at equilibrium, so this is where I'm going to plug in that into my NO. This goes into my N, and this here goes into my oxygen, and guess what? I know my K, it's 1.2. Okay, so let's go ahead and do that here. My K is 1.20, and then my concentration of nitrogen at equilibrium is X. My concentration of oxygen at equilibrium is X, so it's X times X. It's X squared on top. Okay. On the bottom, you guys have NO, so it's 0.667 minus 2x and the square. Okay, so you have a square here. Now, the rest is just algebra, right? You're solving for x, and I will tell you that you're always going to get a situation here mathematically where you're going to have a square on top and a square on the bottom like this, so it's easy to solve. Otherwise, if this were just a plain x on top with a square on the bottom, you would have to use the quadratic formula. And thankfully, you do not have to do that for this class. And you actually don't for the AP test, I found out this year as well. So to get rid of the x's, or the square here and the square here, we could just square root both sides. Okay, so if I square root 1.2, I'm going to get 1.095. And if you just go to 3 decimal places here as you're doing the math, you're fine. X squared becomes x, and I have 0.667 minus 2x. So I just got rid of the square. Now, to get rid of all this on the bottom, I'm going to multiply both sides by it. So I'm going to continue here. I have 1.095. I'm going to multiply by all this on the bottom. 0.667 minus 2x, okay, is equal to x. Okay, so I multiply both sides by this to get that, right? Right, so if we're looking at the rest of the math over here, we want to distribute the 1.095 to the 0.667 and then distribute the 1.095 to the -2. So when you do that, 1.095 times 0.667, you get 0.730. If you go to 3 decimal places, you're good. And then you have -2 times 1.095. So I'm doing that part of the distribution. You end up with minus 2.19x, and it's equal to 1x over on the right side. So I'm just continuing all this out over here. Okay, so we're going to add our x's together. So I'm going to add 2.19x here. Okay. And believe it or not, I think this is the most common mistake that people make. When they see the 2.19x plus x, they don't consider that there's really a 1 right here. So they say it's 2.19x when you know that it should be 3.19x. And on the left side, we have 0.730, right? And to get x all by itself, we're just going to divide by 3.19 and 0.730 divided by 3.19 gives us 0.2288 as our x. And let's check to see how many significant figures we're going to need. 3, 4, so it looks like 3. So 3 is good. So we get 0.229 molarity here for the x. Okay, so what does that tell us? That x is equal to 0.229. So this is going to be 0.229. This is 0.229 as well. And then finally, to get the equilibrium concentration of NO, it's going to be 0.667. So we're just doing that, right? Minus 2 times our x, which was 0.229. and we end up with 0.209 molarity. That's tough to see, but you have 0.209, 0.229, and 0.229 for the equilibrium concentration. So it took a little bit more work here, but that's it. You just have to remember, I think the hardest part is just remembering how to set up this ice chart. And then once you get to the math, you kind of know the steps. And it's always going to be the same. You're going to have to square root both sides because you'll get a square and a square here. Okay. Then you're going to have to distribute out, right? You're going to have to put your variables together. And once you know what your x value is, you could go back and put it in right there. Okay. So that is it. And then sample type problem 4, I'm going to be doing with you guys on Monday. And it's probably actually one of the easier type of problems to do with equilibrium. So you guys should be okay with that. You do have homework over the weekend in addition to the lab. So you have page 463, numbers 19 through 27 odds. So make sure you guys get that done, which is going to be going over how to do these ice chart setups. And that's it. Have a good weekend, everyone. Oh, and don't forget to do the Bright Bytes survey, which I have a link up for on Google Classroom. Thank you.